You think you understand black holes? Here's the uncomfortable truth. You've probably never actually seen one. Neither has anyone else. Let me show you why. Richard Feynman had an uncomfortable habit. Asking questions nobody wanted to hear. Simple ones. Direct ones. The kind that expose the difference between what we actually know and what we think we know. And when it came to black holes, he asked something that made physicists really uncomfortable. How do you actually know that? Think about it. You've seen incredible documentaries about black holes devouring stars. Scientists describe with total confidence what happens at the event horizon. Singularities where the density goes infinite. Time just stops. Hawking radiation pouring out. Sounds scientific. Proven. But here's what Feynman asked. How much of that have we actually observed? And how much did you just accept because the math works out? It's the question nobody asks. But once you start poking at it, the whole house of certainty about black holes starts to fall apart. Because here's the real problem. Almost everything you know about black holes comes from mathematical extrapolations of a theory, not from actually watching them. And Feynman had a big issue with that. He was clear. Physics is an experimental science. You observe, you measure, you be honest about what you actually saw versus what the math says should be there. So what do we actually know about black holes? And what are we pretending to know? Let me show you where the line becomes very, very blurry. We start with what we can actually observe. And that's surprisingly little. When astronomers say they've detected a black hole, what did they really measure? Gravitational effects. Stars orbiting something you can't see. Gas spiraling inward, heating up to millions of degrees, shooting out X-rays before it vanishes. Gravitational waves when two massive objects collide. All of that is real, observable, measurable. But here's what's not on that list. No one has actually observed an event horizon. No one has seen a singularity. No one has measured time stopping. No one has detected Hawking radiation. All those concepts, the things that make black holes what they are in your mind, are theoretical predictions from Einstein's equations. They're what the math says happens when you push the theory to its absolute limits. And this is where Feynman's point gets really important. There's a massive difference between the math says this should happen and we actually watch this happen. Think about it this way. You've got a formula that perfectly predicts how a ball rolls downhill. Test it on small hills? Perfect. Medium hills? Works great. Then you extrapolate to an infinitely tall hill, and the formula says the ball reaches infinite speed. Do you actually believe that? Or do you think something's wrong with your theory before you hit infinity? That's exactly what's happening with black holes. General relativity works great for describing gravity in the solar system. It nails how light bends around the sun. It explains Mercury's orbit perfectly. It describes gravitational waves from colliding neutron stars. Then we take those same equations and push them to the absolute limit. We compress matter to densities that have never existed. We extrapolate to points where the math predicts infinity, and suddenly we're declaring with total confidence that we know what happens. Feynman would stop you right there and say, think about what you're claiming. You're saying you know what happens in a place no experiment can ever reach, based on a theory you know is incomplete. And getting predictions with mathematical infinities which throughout history have always been red flags. How can you possibly know you're right? Honestly, we don't know. We're making an educated guess. The math works where we can test it, so we're hoping it works where we can't. But that's just an assumption, not something we've actually observed. And once you really get that difference, black holes start looking completely different. Let's get concrete here. The most famous thing about black holes: the event horizon. What is an event horizon? It's the boundary beyond which nothing can escape, not even light. Cross it, and you're gone forever. No way to send any signal back. Sounds dramatic. And yeah, it's there in the math. Compute the Schwarzschild radius and you get where the horizon is. The math checks out. But here's Feynman's question. How would you actually confirm that this horizon exists? Think about it. To confirm a horizon exists, you'd need to cross it and report back. But if you cross it, you can't report back. And if you can report back, you never crossed it. Perfect paradox. The definition itself makes it impossible to verify directly. You might argue, But we see matter disappearing as it falls toward black holes. Doesn't that prove a horizon exists? No. You're watching matter radiate as it gets hot and accelerates. You're watching that light fade as it gets closer to something massive. Eventually, it's too faint to see. But too faint to see is not the same as it crossed a one-way boundary. It's just the limit of what you can observe. Feynman was obsessed with the difference between what you can observe and what you're claiming about reality. If you can't see something, fine, say, I can't see it. But don't claim it crossed a one-way boundary into a place where nothing escapes. One is honest about the limits. The other is a theory pretending to be fact. Now it gets really weird. This is where the math gets really strange, and where Feynman's point about theory versus observation becomes absolutely crucial. According to general relativity, time slows down in strong gravity. The stronger the gravity, the slower time moves compared to a distant observer. As you get close to the event horizon of a black hole, time dilation becomes insane. Now, see what that means from the perspective of an outside observer, you, watching from a safe distance. Watch a star falling toward a black hole. As it gets closer, the star seems to slow down. You see it moving slower and slower. The light shifts to longer wavelengths as it fights against the intense gravity. The closer the star gets to the horizon, the slower its time gets. And mathematically, from your perspective way out here, it would take forever for the star to actually cross the horizon. Stop right there. Think about that. From your perspective, the only one you actually have as an outside observer, nothing ever crosses the horizon. Ever. Matter just freezes, getting closer and closer but never actually reaching it. That's why black holes were originally called frozen stars, before black hole became the catchy name. Because from the perspective of anyone who can actually tell you what they see, nothing ever falls all the way in. You might say, but from the falling star's perspective, it crosses the horizon in finite time. The math says yes. From the falling object's perspective, assuming the equations work there, it crosses quickly. But here's where Feynman's point gets uncomfortable. You can never have that perspective. By definition, once it crosses, it can't talk to you. So anything you claim about that perspective is pure theory. You're trusting the equations to work in a place that can never be observed. And from the only perspective you can actually have, nothing has ever fallen into a black hole since the Big Bang. Think about that. Take time dilation seriously, and from our perspective, all matter that fell into black holes is still frozen just above the horizon, getting closer but never crossing. What does that do to the whole idea of black holes as cosmic vacuums that gulp down billions of solar masses? From our perspective in time, they haven't swallowed anything. Not yet. That doesn't mean black holes aren't real or dangerous. The gravity is absolutely real. Get too close and you're dead. But the story matter crossing the horizon and falling into the singularity, that's theory, not something we've observed or could observe from here. And Feynman would be relentless about that distinction. So if the story about the event horizon is shaky from our view, what about the center of a black hole, the singularity? Now it gets even more problematic. In general relativity's equations, push matter beyond the horizon and it keeps collapsing. Nothing stops it. It collapses until all the mass gets squeezed into a point of zero volume and infinite density. That's a singularity, infinity, right there in your physics. And here's the thing, infinities in physics are always a red flag that your theory is broken. Feynman knew this from experience. He spent years wrestling with infinities in quantum electrodynamics, the work that won him the Nobel Prize. The equations kept producing infinities, but Feynman and others realized those infinities were artifacts of pushing the theory beyond where it worked, into regions where quantum effects you hadn't included mattered. The solution was renormalization, which basically says, our theory is incomplete at tiny scales. So let's stop pretending we know what happens there and focus on what we can actually calculate. And it worked, because they were honest about what their theory could do. So what happens when we apply that lesson to black holes? With black holes, we do the opposite. We take a theory, push it into regions where it predicts infinity, and then claim those infinities are real features of the universe. That's really suspicious. Every time in physics history that an equation produced infinity, it turned out the theory was incomplete, not that the universe actually had infinities. Classical equations said electrons should spiral into the nucleus instantly, releasing infinite energy. That wasn't real. It meant classical physics was broken. Quantum mechanics fixed it. Early quantum electrodynamics predicted infinite particle energies. Not real. The theory needed fixing. When general relativity predicts infinite density in black holes, it probably means the theory is incomplete there. Not that the universe actually has infinities. We know its incomplete general relativity doesn't include quantum mechanics. At tiny scales and extreme densities, quantum effects have to matter. So what's actually at the center of a black hole? Honestly, we don't know. General relativity predicts a singularity, but it's probably wrong. Quantum gravity. The theory combining both would probably give a different answer, but we don't have a complete theory of quantum gravity yet. So we're making educated guesses, using the math to extrapolate, but we're not observing, not measuring, definitely not knowing. Feynman would be crystal clear. When you don't know something, say so. Don't hide ignorance behind fancy math. And this goes way beyond singularities. Let's talk about Hawking radiation. You've probably heard the name. It's Hawking's prediction that black holes aren't actually black. Quantum effects near the horizon should make them emit radiation and eventually evaporate. It's beautiful theoretical physics. Combines general relativity and quantum mechanics in an elegant approximation. Impressive math. But here's the problem. We've never actually observed it. No one has detected Hawking radiation from an actual black hole. Probably never will, because the predicted temperature for stellar mass black holes is incredibly low, way below the cosmic microwave background. So Hawking radiation is a cool, theoretical prediction that'll probably never be tested on real black holes. And that's fine, if you're honest. It's a theoretical exploration of how gravity and quantum mechanics might work together. Educated speculation based on solid principles. But not something we've observed. Same with the information paradox, the internal structure. Whether black holes have hair, complementarity, firewalls, the whole bunch of theoretical ideas about what happens near and inside event horizons. All fascinating math, but they're speculations, not observations, and it matters. Because when you treat speculations as facts, you stop asking the real questions. You stop looking for where the theory breaks. You build increasingly complex math on untested foundations. Feynman saw this everywhere and always pushed back. How do you know? What did you actually measure? What are you assuming? Uncomfortable questions because they expose how little we actually know, but essential for honest science. So what's the lesson? Feynman's not saying black holes are fake or theory is worthless. He's saying something subtler and more important. Your confidence should match your evidence. When you observe gravity from an invisible, massive object, you can be confident something dense is there. Strong evidence. Gravitational waves from mergers, X-rays from accretion disks, stars orbiting Sagittarius A, all pointing to incredibly compact, massive objects. You can reasonably trust that general relativity describes those objects in regions you can test outside the extremes. But start making claims about the event horizon or singularity and your confidence should plummet. You're extrapolating into regions that have never been and might never be tested. That doesn't mean these ideas are worthless. They give useful frameworks. They make predictions with indirectly testable consequences. They inspire new math and experiments. But they're not facts. They're hypotheses. Good ones, mathematically solid, but still hypotheses. And Feynman would say being honest about the limits. Having intellectual humility is essential to good science. Because the history of physics is full of theories that worked great until they didn't. Newtonian physics is perfect for everyday speeds, but breaks near light speed. Classical mechanics works for big objects, fails at atomic scales. And general relativity probably works in testable regimes, but breaks at the extremes. That's not weakness. That's wisdom. It means your theory might be incomplete. You're actively looking for where it breaks. You'll revise it when evidence shows up. And crucially, you're not lying to yourself or others about what you know versus what you're guessing. Feynman had a core principle. The first rule is you can't fool yourself, and you're the easiest person to fool. And here's the key point. With black holes, it's easy to fool yourself. The math is beautiful. Predictions are dramatic. The logic feels perfect. But reality doesn't care how elegant your theory is. And history shows the universe is always stranger than we predict. Yes, black holes are real. real gravity, real observable effects. But most of what you think you know, event horizons, singularities, Hawking radiation, the interior is theory. Beautiful math applied way beyond where it's been tested. And Feynman's lesson is, keep those separate. Observe, measure, calculate, be honest about what is what. Because at the end of the day, physics isn't about pretty equations. It's about understanding reality, and you only understand what you actually observe, measure, and test. Everything else is speculation, sometimes good speculation, still speculation. And that difference matters. Next time someone speaks with total confidence about what happens inside a black hole, ask Feynman's question, how do you know that? And if they say, the math says so, remember, the math also said electrons should spiral into the nucleus. Particles should have infinite energy. The math has said a lot of things that turned out to be wrong. Math is a tool, powerful tool. But it's not reality. Confusing the map with the territory is exactly what Feynman fought against. So be curious, be skeptical, ask tough questions, demand evidence, know the difference between what's observed and what's assumed. That's the method Feynman advocated. And it goes beyond black holes. It applies to any science claim, any theory, any claim of knowledge you run into. The universe is strange. Wonderfully, gloriously strange. Stranger than we imagine. But you truly know it when you're rigorous about what you know, how you know it, and where it turns into speculation. That's Feynman's gift. Not definitive answers, but relentless questions asked right. Always ask, what was actually observed? What's extrapolation? How strong is the evidence? Apply that critical thinking and you'll understand science better. You'll understand how real knowledge actually works in your life. And when you can separate what's observed from what's assumed, when you can question like Feynman, everything changes. This thinking transforms how you see black holes, how you see any truth claim in the world. If rigorous questioning resonates with you, if you want to understand not just what to think, but how to think, subscribe. We explore the big questions with the intellectual honesty Feynman championed. And if you want to go deeper, if these ideas hit you, comment on which part challenged you most. Let's